So now that we calculated the measured SIRs initially, or for iteration 0, we can go on to calculate the new power levels for the first iteration, or iteration 1, and subsequently the new signal to interference ratios that those power levels imply. And so, if we remember, the update for the power levels was equal to the desired over the measured SIR times the current power level. And so we can go down for each of those transmitters and first calculate this term, this desired over measured, which we called the ratio before. And we can use that then to calculate the new power levels. So for the first link, as we see down here, we have a target SIR of 1.8, and so that's our desired. And our measured SIR is about 2.27, and so this comes out to be about 0.7. And so that's saying that we were 70%. We want to cut back our level by 70% because we were too high before. And for link 2, we saw before we have a desired SIR of 2.0, and we had measured 2.67, and so that gives us about 0.75, and so that means we want to reduce by about 25%, or we want to take 75% of what we had before. And for link 3, we have a desired of 2.2, and we want to divide that by what we had measured, which was 1.64. And so now we're going to get a value that's greater than 1 of 1.34, which means that we have to increase the power level. And so this, if we do 0.7 for transmitter 1 times 2, which is the initial transmit power, we get 1.4 milliwatts to be the next transmit power. And here we're going to do 0.75 times 2, and that's going to give us 1.5 milliwatts as the second power. So you see these are cut back from 2 accordingly. And for this one, we are going to get 1.34 times 2, which is 2.68 milliwatts, respectively. So that's how we update the power levels. And now, with that new information, we can go back and we can recompute the SIRs. And so if you remember, again, our equation for SIR was the signal over the interference plus the noise. And so now we can use that again with these new power levels instead. But the gain parameters and the noise values that we're going to use here all stay the same. So for link 1, we have 0.9, which is the direct channel gain, times the new power level, which is 1.40, over the interference, which was 0.1. This is the interfering gain for link 1 again, times 1.5 plus 0.2 times 2.68. And so we can pause here to remember that these values now, this 1.4 that we're using, this 1.5 that we're using, and this should be a plus, and this 2.68 that we're using are all different now because those are all the new power levels that we're using, whereas in the previous equation for iteration 0, we started with the same power level for everyone. But now that's not the case, everyone. Now the power levels are different, so they have different values in this equation, plus the noise here, which is 0.1. And doing that out, we get 1.60 to be that SIR for number 1. For number 2, we have a direct gain of 0.8. We want to multiply that by 2's power level of 1.5. And then we want to use the interfering channel gains of 0.1 and also 0.1. So they're both 0.1. 0.1 times 1.4 plus 0.1 times 2.68. And then we want to add the noise in that receiver of 0.2. And when we compute that, we get 1.97. And so now, as you can see, these SIRs are actually too low for 1 and 2, whereas before they were too high. So they've reversed direction now. So now we went in too far in the opposite direction. And for link 3, we have 0.9 times 2.68 direct over interfering, which would be these 0.2 values. 0.2 times 1.4 plus 0.2 times 1.5 plus the noise, which was 0.3, and that comes out to be 2.75. And that is now too high, higher than what it was before. And so you can see that before, again, we reversed directions here, because before these were too high, and now they're too low. And before this was too low, and now this is too high. And that's a pattern of what we call overshooting. So right now, we overshot the value for link 3, but we undershooting for links 1 and 2. And that pattern of overshooting, undershooting, and then switching between the two throughout iterations will likely keep going on until we converge on power levels. So we go too high, and then we go too low, and then go too high and too low, and so on.